Our solar system. Act 1. The engine of everything. At the very heart of our cosmic neighborhood, there exists a sphere of light and energy so vast, so powerful, that everything we know, everything we see in our night sky, every planet, every moon, every speck of dust orbits around it in an endless, graceful dance. This is our sun. And while we see it rise and set each day, while we feel its warmth on our skin and watch its light paint our world in gold, there is so much more to this magnificent star than meets the eye. The sun is what astronomers call a yellow dwarf star. It's a classification that might sound humble, almost modest, but don't let the name fool you. This yellow dwarf is anything but small. In fact, the sun contains an almost incomprehensible amount of the matter in our entire solar system. When scientists calculated the total mass of everything that orbits within our sun's gravitational embrace, every planet, every asteroid, every comet, every particle of ice and rock and gas, they discovered something remarkable. The sun alone accounts for 99.86% of all that mass. Think about that for a moment. All 8 planets combined, from tiny Mercury to giant Jupiter, along with their moons and rings, all the asteroids in the belt between Mars and Jupiter, all the icy objects in the distant Kuiper belt, everything together makes up less than 1/7 of 1% of our solar system's total mass. The sun is truly the gravitational anchor, the central pillar upon which our entire cosmic home is built. But numbers can be abstract, difficult to truly grasp. So let's try to visualize the sun's immensity in a different way. Imagine our Earth, this world we call home, with all its oceans and continents, its mountains reaching toward the sky and valleys carved deep into its crust. Now imagine you could somehow hollow out the sun and begin filling it with Earth-sized spheres, packing them in one after another. How many do you think would fit? 1,000? 10,000? The answer is even more staggering. You could fit approximately 1.3 million Earths inside the volume of the sun. 1,300,000 worlds the size of ours, all fitting within that glowing sphere we see in our daytime sky. It's a scale that challenges our imagination, that reminds us just how small we are in the grand theater of space. And yet, for all its size, the sun's true power lies not in its volume but in what happens deep within its core. At the very center of our star, crushed under the weight of hundreds of thousands of miles of stellar material pressing down from all sides, exists a realm of unimaginable temperature and pressure. Here, in this nuclear furnace, the temperature soars to 15 million degrees Celsius. To put that in perspective, the surface of the sun is a relatively cool 5,500 degrees. But the core, the heart of our star, is nearly 3,000 times hotter. At these extreme temperatures and pressures, something extraordinary occurs. Hydrogen atoms, the simplest and most abundant element in the universe, are forced together with such intensity that they fuse, combining to create helium and releasing tremendous amounts of energy in the process. This is nuclear fusion, the same process that powers hydrogen bombs here on Earth, but on a scale that defies comprehension. Every single second, the sun's core produces energy equivalent to 100 billion hydrogen bombs exploding simultaneously. Every second. And this has been happening day and night for the past 4.5 billion years. It's this continuous fusion reaction that creates the light and heat that makes life possible on our distant world. When you step outside on a sunny day and feel the warmth on your face, when you see the blue sky above and the green leaves of trees, you're experiencing energy that began its journey in the sun's core. But that journey takes time. The light particles, the photons created in those fusion reactions deep inside the sun, don't immediately zip out into space. Instead, they begin a long, chaotic journey outward, bouncing and scattering through the dense stellar material, taking anywhere from 10,000 to 170,000 years to finally reach the sun's surface. But once they break free into the vacuum of space, they travel at the ultimate cosmic speed limit, the speed of light, racing outward at nearly 300,000 kilometers per second. And even at this incredible velocity, it still takes time to cross the vast gulf of space between the sun and Earth. The light you see when you look outside right now, the sunlight streaming through your window or reflecting off the world around you, that light took roughly 8 minutes and 20 seconds to travel from the sun to your eyes. You're seeing the sun not as it is in this exact moment, but as it was a little over 8 minutes ago. You're looking backward in time, seeing our star's very recent past. There's something else interesting about the light the sun produces, something that surprises many people when they first learn it. We call the sun a yellow star. We draw it as a yellow circle in children's books, and when we look up at it in the sky, it certainly appears to have a yellowish hue. But here's a fascinating truth. The sun isn't actually yellow at all. In the vacuum of space, viewed from above Earth's atmosphere, the sun appears white. Pure, brilliant white. The reason we see it as yellow from the ground is because of our planet's atmosphere. As sunlight enters the upper reaches of our atmosphere and travels down toward the surface, it passes through layers of gases, nitrogen and oxygen and others. These gases scatter the shorter wavelengths of light, the blues and violets, spreading them across the sky and giving us our beautiful blue daytime canopy. What remains on the direct path from the sun to our eyes is weighted more heavily toward the yellows and reds, creating that familiar golden appearance. But in its true nature, our sun shines with the combined light of all colors, which our eyes perceive as white. The sun itself is not a simple sphere with a clean, defined edge. Like Earth, it has an atmosphere, though one quite different from our own. The sun's atmosphere is divided into layers, each with its own characteristics and mysteries. The visible surface we see, called the photosphere, is where most of the light we receive originates. Above this lies a thin reddish layer called the chromosphere, and above that extends the corona, a vast halo of extremely thin, hot gas that stretches millions of kilometers into space. And here's where things get truly strange. You might reasonably expect that as you move away from the sun's blazingly hot surface, temperatures would drop. And at first they do. The chromosphere is cooler than the photosphere below it. But then something unexpected happens. The corona, despite being much farther from the sun's core, is dramatically hotter than the surface beneath it. While the photosphere has a temperature of about 5,500 degrees Celsius, the corona reaches temperatures of 1 to 3 million degrees Celsius. This is one of the great mysteries of solar physics, something scientists call the coronal heating problem. How can the outer atmosphere be so much hotter than the surface below? Researchers believe it has to do with magnetic fields that thread through the sun's atmosphere, carrying energy outward and releasing it in the corona through complex processes we're still working to fully understand. It's a reminder that even our closest star, one we've studied for centuries, still holds secrets waiting to be unraveled. The sun's influence extends far beyond the light and heat it provides. Our star is constantly releasing matter into space, a stream of charged particles, mostly electrons and protons, flowing outward in all directions. This is called the solar wind, and it races away from the sun at speeds ranging from about 300 to over 800 kilometers per second. This invisible river of particles fills our solar system, washing over every planet, every moon, every object in its path. When Earth lies in the path of the solar wind, Most of these particles are deflected by our planet's magnetic field, which acts like a protective shield. But near the poles, where the magnetic field lines dive down toward the surface, some of these charged particles can enter our atmosphere. There they collide with atoms of oxygen and nitrogen high above the ground, exciting these atmospheric atoms and causing them to glow. This creates the dancing curtains of light we call the aurora borealis in the north and aurora australis in the south, the northern and southern lights. But Earth isn't the only world graced with auroras. These cosmic light shows occur on other planets too. Jupiter, with its powerful magnetic field, hosts auroras far more intense than anything on Earth. Saturn has its own auroral displays shimmering at its poles. Even distant Uranus and Neptune, those ice giants orbiting in the outer reaches of our solar system, experience auroras as the solar wind interacts with their magnetic fields. The sun's reach extends to every corner of our cosmic neighborhood, connecting all the worlds in a web of magnetic fields and particle streams. But the sun, for all its power and constancy, is not eternal. Stars, like all things in the universe, have life cycles. They are born from collapsing clouds of gas and dust. They live out their lives burning through their nuclear fuel, and eventually they die. Our sun is currently in the middle of its life, in a stable phase that has lasted for billions of years and will continue for billions more. But eventually, approximately 5 billion years from now, the sun will begin to change. The hydrogen fuel in its core will become depleted, and the fusion reactions that have powered our star for so long will begin to falter. Without the outward pressure from fusion to balance gravity's inward pull, the core will begin to contract and heat up. This increased temperature will ignite hydrogen fusion in a shell around the core, and the energy from this shell burning will cause the sun's outer layers to expand dramatically. Our star will swell into what astronomers call a red giant, growing so large that its outer atmosphere may extend beyond Earth's current orbit. Mercury, the innermost planet, will almost certainly be consumed, swallowed by the expanding stellar envelope. Venus, second from the Sun, will likely meet the same fate. And Earth, our home, sits right on the edge of uncertainty. Some models suggest our planet will be engulfed as well. Others indicate that changes in the Sun's mass as it loses its outer layers might cause Earth's orbit to drift outward just enough to escape destruction. But even if our planet physically survives, it will be a world transformed beyond recognition, its surface scorched to a lifeless cinder by the intense heat of the nearby giant star. Of course, this transformation lies billions of years in the future, an almost incomprehensible span of time ahead. For now and for ages to come, the sun will continue its steady work, rising and setting, powering the cycles of life on our world, holding our solar system together with its gravity and filling space with its light. It is, in every sense, the engine of everything, the central fire around which our cosmic story unfolds. Act 2. The rocky inner circle. Now that we've explored the sun, the great engine at the center of our solar system, let's begin a journey outward, moving through the inner realm of our cosmic neighborhood. Here, in the region closest to the sun's warmth and light, orbit 4 worlds quite different from the giants that lie beyond. These are the terrestrial planets, the rocky worlds, each one a sphere of metal and stone shaped by heat and time and the violent forces of planetary formation. And our journey begins with the smallest and swiftest of them all. Mercury, the innermost planet, races around the sun at speeds that put all other worlds to shame. While Earth takes 365 days to complete one orbit, Mercury whips around our star in just 88 Earth days. 88 days for an entire year on Mercury. This incredible speed is a consequence of its proximity to the Sun. The closer a planet orbits to a massive body, the faster it must travel to maintain its orbital balance, and Mercury, being the closest planet to our star, moves through space at an average velocity of nearly 48 kilometers per second. That's over 170,000 kilometers per hour. To put that in perspective, Earth travels at a more leisurely 30 kilometers per second. Mercury is quite literally the speedster of our solar system, forever locked in its rapid dance around the Sun, completing orbit after orbit while the outer planets lumber slowly through their much longer celestial paths. But despite its speed, or perhaps because of its closeness to the Sun, Mercury is a world of extremes that would be utterly hostile to any visitor. You see, Mercury lacks something that most other planets possess, something we often take for granted here on Earth. Mercury has no atmosphere. No protective blanket of gas surrounds this small world. Without an atmosphere to trap and distribute heat, to shield the surface from radiation, or to moderate temperature swings, Mercury experiences some of the wildest weather variations in the entire solar system. During its day, when the Sun hangs in Mercury's sky blazing down on the barren landscape, surface temperatures soar to a scorching 430 degrees Celsius. That's hot enough to melt lead, hot enough to turn certain metals into liquid puddles. But Mercury rotates very slowly on its axis. In fact, one day on Mercury from one sunrise to the next takes 176 Earth days. So the night is long, and without an atmosphere to hold the heat, temperatures plummet. On the night side of Mercury, away from the Sun's rays, the temperature drops to a freezing negative 180 degrees Celsius. From 430 above zero to 180 below zero. A swing of over 600 degrees between day and night. It's a temperature range more extreme than anywhere else we know, a testament to how important an atmosphere is for maintaining stable conditions on a planetary surface. Mercury is also a small world, the smallest true planet in our solar system since Pluto was reclassified. When you look at Mercury beside our Moon, you might be surprised at how similar they are in size. Mercury is only slightly larger than Earth's Moon, with a diameter of about 4,880 kilometers compared to the Moon's 3,475. And like the Moon, Mercury's surface is covered with impact craters, scars from billions of years of collisions with asteroids and comets. But there's something happening to Mercury that makes it unique among the planets. It's shrinking. As Mercury's large iron core slowly cools over geological time, it contracts, and this contraction causes the entire planet to shrink ever so slightly. The surface wrinkles and buckles, forming long cliff-like features called scarps that can stretch for hundreds of kilometers across the landscape. These scarps are evidence of a world in decline, a planet gradually growing smaller as the eons pass, its internal heat slowly radiating away into the cold vacuum of space. Moving outward from Mercury's scorched surface, we come to the second planet, a world that has captured human imagination for millennia with its brilliant appearance in our evening and morning skies. Venus, named after the Roman goddess of love and beauty, shines brighter than any star in Earth's night sky, a gleaming beacon that has guided travelers and inspired poets throughout human history. And there's a reason Venus appears so bright. It's close to Earth, and it's nearly the same size as our home planet, with a diameter of about 12,100 kilometers compared to Earth's 12,742. Because of this similarity in size, Venus is often called Earth's sister planet or Earth's twin. But this is a case where appearances are deeply deceiving. Venus may look like Earth's twin from afar, but up close, it's a world of such extreme hostility that it makes Mercury's temperature swings seem almost gentle by comparison. Venus holds a dark distinction. It is the hottest planet in the entire solar system. Not Mercury despite being closer to the Sun, but Venus. The surface temperature on Venus averages around 460 degrees Celsius, and unlike Mercury, this temperature remains fairly constant across the entire planet, day and night, equator and poles. The reason for this infernal heat is Venus's atmosphere, and what an atmosphere it is. The Venusian atmosphere is incredibly thick, composed almost entirely of carbon dioxide, and it presses down on the surface with a crushing weight 92 times greater than Earth's atmospheric pressure at sea level. Standing on the surface of Venus would feel like being nearly a kilometer underwater here on Earth. But it's not just the pressure. That thick carbon dioxide atmosphere creates what scientists call a runaway greenhouse effect. Carbon dioxide is very good at trapping heat, and Venus has so much of it that sunlight can enter the atmosphere and warm the surface, but the heat cannot escape back into space. It's trapped, building up over millions of years until the entire planet became a furnace. The clouds that shroud Venus and give it such a bright appearance from Earth are not made of water vapor like our clouds. They're composed of sulfuric acid, corrosive droplets that rain down through the upper atmosphere only to evaporate in the intense heat long before reaching the surface. Venus is a cautionary tale about greenhouse effects, a reminder of what can happen when atmospheric conditions spiral out of control. And Venus has other peculiarities that set it apart. If you could somehow survive on Venus's surface and look up to see the sun rising, you would notice something very strange. The sun would rise in the west and set in the east, the opposite of what we experience here on Earth. Venus is one of only 2 planets in our solar system that rotates clockwise when viewed from above its north pole. All the other planets, with the exception of Uranus, rotate counterclockwise. Why Venus spins in this retrograde direction remains something of a mystery, though scientists believe it may have been caused by a massive collision early in the planet's history that literally knocked it spinning in the opposite direction. And if that wasn't unusual enough, Venus rotates extremely slowly. One full rotation takes 243 Earth days. But Venus orbits the Sun in only 225 Earth days. This means that a day on Venus, one complete rotation, actually takes longer than a Venusian year. Time works very differently on our sister planet, where days outlast years and the Sun moves backwards across the sulfuric sky. Continuing our journey outward, we arrive at a place of profound significance. The third planet from the Sun. Our home. From space, Earth appears as a beautiful blue and white marble suspended against the black velvet of space, swirled with white clouds, its continents tinged brown and green, its vast oceans a deep, rich blue. And that blue is the key to everything that makes Earth special. Our planet is the only world we know of that has liquid water on its surface. Oceans, lakes, rivers, streams. Water in its liquid form is essential for life as we understand it, and Earth has it in abundance. About 71% of Earth's surface is covered by oceans, great bodies of water that regulate our climate, drive our weather patterns, and provide habitat for countless forms of life. But water alone isn't enough. Earth also has an atmosphere, a protective envelope of gases that shields us from harmful radiation, maintains temperatures in a range where water can remain liquid, and provides something else absolutely critical: oxygen. 21% of Earth's atmosphere is oxygen, a highly reactive gas that most life on our planet needs to survive. this oxygen wasn't always present. Early in Earth's history, the atmosphere contained almost no oxygen at all. It was the rise of photosynthetic organisms, first simple bacteria and later plants, that slowly transformed our atmosphere over billions of years, pumping out oxygen as a byproduct of their metabolism. And that oxygen, in turn, allowed for the evolution of complex animals, creatures that could burn food with oxygen to generate the energy needed for active, mobile lifestyles. We are, in a very real sense, living within the creation of ancient life forms that remade our planet's atmosphere. Earth has another feature that helps make it habitable: a magnetic field. Deep within our planet lies a core made primarily of iron and nickel. This core has two parts: a solid inner core and a liquid outer core. The solid inner core, despite being under immense pressure, is incredibly hot, approximately 5,200 degrees Celsius. That's roughly the same temperature as the surface of the sun, an inferno buried thousands of kilometers beneath our feet. This heat is a remnant of Earth's formation, when countless collisions between rocky bodies released tremendous energy, and it's also generated by the radioactive decay of elements within the Earth. The liquid outer core swirls and flows around the solid inner core, and because it's made of iron and nickel, both of which conduct electricity, this motion generates electric currents. Those electric currents, in turn, create a magnetic field that extends far out into space around our planet. This magnetic field is invisible to us, but it's vitally important. It deflects the solar wind, that stream of charged particles constantly flowing from the sun, preventing it from stripping away our atmosphere. It protects us from harmful cosmic radiation. Without this magnetic shield, Earth might have ended up more like Mars, a cold, dry world with a thin atmosphere, unable to support the rich tapestry of life we see around us. And speaking of Mars, our journey through the inner solar system brings us finally to the fourth and final terrestrial planet, the red planet, Mars. Even with the naked eye, Mars appears distinctly reddish in the night sky, a color that ancient civilizations associated with blood and war, leading them to name it after the Roman god of war. But there's nothing mystical about Mars's color. It comes from something quite mundane: iron oxide. The Martian surface is rich in iron, and over billions of years, that iron has reacted with the small amounts of oxygen in Mars's thin atmosphere, oxidizing and turning a rusty red color. The entire planet is essentially covered in rust, giving it that distinctive hue we can see from Earth with our own eyes. Fine particles of this rust are also lofted into the Martian atmosphere by winds, sometimes creating planet-wide dust storms that can obscure the surface for months at a time. Mars is a world of superlatives, home to some of the most dramatic geological features in the entire solar system. Consider Olympus Mons, a volcano so large it defies easy comparison. Standing about 22 kilometers high, Olympus Mons is nearly 3 times the height of Mount Everest, Earth's tallest mountain. But unlike Everest, which is part of a mountain range pushed up by tectonic forces, Olympus Mons is a shield volcano, built up over millions of years by lava flows that spread out in all directions from a central vent. Its base is so wide, covering an area roughly the size of Italy, that if you stood on its slopes, you wouldn't even realize you were on a mountain. The incline is so gentle, the volcano so enormous, that the horizon would hide its true shape from you. And Olympus Mons is not alone. Mars has several other massive volcanoes, all long extinct now, but evidence of a time when the red planet was geologically active, when molten rock flowed across its surface and volcanic eruptions shaped the landscape. Near these volcanic regions lies another Martian marvel, Valles Marineris, a canyon system so vast it makes Earth's Grand Canyon look like a mere scratch in the dirt. Valles Marineris stretches over 4,000 kilometers across the Martian surface. To put that in perspective, if you place this canyon on Earth, it would span nearly the entire width of the United States. In places, it reaches depths of 7 kilometers, and its width can exceed 200 kilometers. We're not entirely sure how Valles Marineris formed, though it likely began as a crack created when the region around it bulged upward billions of years ago, and was then widened and deepened by subsequent erosion and landslides. Walking along the rim of Valles Marineris, you would see cliffs and walls stretching to the horizon in both directions, a scar on Mars that speaks to the violent geological forces that once shaped this now quiet world. And if you were standing on Mars, perhaps near the rim of that great canyon, and you waited for evening to arrive, you would witness something both familiar and strange. As the sun began to set in the Martian sky, as its light dimmed and the day turned toward night, the colors around the sun would shift. But instead of the warm reds and oranges we associate with sunsets on Earth, a Martian sunset would appear blue. Blue around the sun, fading to reddish-brown farther from it. This reversal happens because of the fine dust suspended in Mars's atmosphere. On Earth, our atmosphere scatters blue light, making our sky blue and our sunsets red. But the Martian dust particles are just the right size to scatter red light more effectively than blue. During the day, this gives Mars a butterscotch-colored sky. But during sunrise and sunset, when sunlight has to travel through more atmosphere to reach your eyes, the red light is scattered away, and the blue light comes through, creating that eerie blue glow around the sun. It's one more reminder that Mars, for all its similarities to Earth, for all the dreams we have of one day walking on its surface, is truly an alien world, a place where even something as simple as a sunset follows different rules. These 4 worlds, Mercury, Venus, Earth, and Mars, make up the inner solar system. They are the rocky planets, the terrestrial worlds, each one forged in the heat of the young solar system from metal and stone. They are small compared to the giants that orbit farther out, but they are diverse beyond measure. From Mercury's scorched and frozen surface to Venus's crushing, acidic hell, from Earth's life-giving oceans and atmosphere to Mars's rusty deserts and towering volcanoes, each of these worlds tells its own story, shaped by its distance from the sun, its size, its composition, and the accidents of its formation billions of years ago. And as we stand on Earth, looking outward at our neighbors, we can't help but wonder about our place in this cosmic arrangement, about how fortunate we are to live on this one blue world where conditions align so perfectly for life to flourish. Act 3: The Great Divide. As we leave Mars behind and continue our outward journey through the solar system, we enter a region that serves as a boundary, a great divide between 2 very different realms. Behind us lie the small, rocky terrestrial planets, huddled close to the sun's warmth. Ahead of us wait the gas giants, enormous worlds of swirling clouds and powerful storms orbiting in the cold outer reaches of our cosmic neighborhood. But between these 2 domains, spanning a vast region of space, lies something that might seem at first to be empty. It is not. This is the realm of the asteroid belt, a zone stretching from roughly 329 million kilometers from the Sun to as far as 478 million kilometers out, a band of space filled with millions upon millions of rocky fragments, the leftover building blocks of planet formation that never quite managed to come together into a world of their own. When most people hear the term asteroid belt, they might picture a dense field of tumbling rocks, a dangerous obstacle course that spacecraft must carefully navigate to avoid collisions, the way it's often shown in science fiction movies. But the reality is quite different and in some ways even more fascinating. The asteroid belt is vast, truly vast, and while it contains millions of objects, most of them are actually quite small, and the distances between them are enormous. If you were somehow transported to the asteroid belt and looked around, you would see mostly empty space, with the occasional glint of reflected sunlight from a distant rock. The largest asteroids would appear as tiny points of light against the stars, and you might go days or weeks without seeing one pass nearby. The belt is not dense or crowded. It is sparse, a diffuse collection of debris spread across a volume of space so large that all the asteroids combined, if you gathered them together, would make a body smaller than our moon. These are the remnants of what might have been another planet in the early solar system, material that began to clump together through gravitational attraction but was prevented from forming a full planet by the immense gravitational influence of nearby Jupiter, whose powerful pull stirred up the region, causing collisions that shattered partially formed bodies rather than allowing them to grow. And so the asteroids remain, fragments of a planet that never was, silently orbiting the sun in the space between worlds. But among these millions of fragments, one object stands out: Ceres. For a long time, Ceres was considered simply the largest asteroid, the king of the belt. And it certainly earned that title. Ceres contains approximately 1/3 of the entire mass of the asteroid belt, a remarkable concentration considering how many objects orbit in this region. But as our understanding of the solar system has grown, as our spacecraft have visited Ceres and examined it up close, we've come to realize that it's something more than just a big asteroid. Ceres is round, shaped by its own gravity into a sphere, and it has a complex interior structure with a rocky core, a thick mantle that may contain large amounts of water ice, and a thin, dusty crust. In 2006, when astronomers created a new classification system for solar system objects, Ceres was promoted, or perhaps more accurately reclassified, as a dwarf planet, joining Pluto and several other bodies in this category. It is the only dwarf planet in the inner solar system, the closest such object to the Sun, and it represents a sort of intermediate stage between the small irregular asteroids and the fully formed planets. Ceres has even shown signs of geological activity. NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, discovered bright spots on its surface that turned out to be deposits of salt left behind by water that had seeped up from below and then evaporated. There may be a global ocean of liquid water beneath Ceres's surface, locked under kilometers of ice and rock. This tiny world, this fragment that never became a planet, might harbor one of the ingredients necessary for life, hidden away in the darkness between the inner and outer solar system. But before we continue outward, before we cross the asteroid belt entirely and enter the realm of the giants, we should turn our attention back to something closer to home. Something we see in our sky nearly every night. Our moon. Earth's constant companion. The moon is so familiar to us that we rarely stop to think about how remarkable it is, or how it came to be. Many planets have moons, of course, but Earth's moon is unusually large relative to the size of its parent planet. Most moons in the solar system are tiny compared to the worlds they orbit, but our moon has a diameter more than a quarter that of Earth. It's so large, in fact, that some astronomers prefer to think of the Earth-Moon system as a double planet rather than a planet with a satellite. And the moon's origin story is one of violence and collision, a tale written in the rocks that astronauts brought back from the lunar surface. Scientists now believe that the Moon was formed about 4.5 billion years ago, early in Earth's history, when our planet was still young and hot, its surface a molten ocean of rock. At some point during this chaotic period, another planetary body, roughly the size of Mars, was on a collision course with Earth. This object, which scientists have named Theia after the Greek Titaness who was the mother of the moon goddess Selene, slammed into the young Earth in a cataclysmic impact. The energy released would have been beyond comprehension, enough to vaporize rock and send tremendous amounts of material spraying out into space. Some of this debris rained back down onto Earth, but a significant portion was thrown into orbit around our planet. Over time, this orbiting ring of vaporized and molten rock began to cool and clump together under its own gravity, eventually coalescing into a single large body, the Moon. This theory, called the giant impact hypothesis, explains many of the Moon's unusual characteristics. It explains why the Moon has relatively little iron compared to Earth, since Theia's iron core would have sunk down and merged with Earth's core during the collision, while the ejected material came primarily from the mantles of both bodies. It explains why the Moon is so large compared to Earth. And it explains why analysis of lunar rocks shows that their composition is remarkably similar to Earth's mantle. The Moon is, in a very real sense, a piece of Earth that was torn away and reformed in orbit, a cosmic sibling born from violence. Those rocks that astronauts collected during the Apollo missions, those precious samples brought back from another world, revealed many secrets about the Moon's history and composition. But they also revealed something unexpected, something that the astronauts themselves noticed immediately upon returning to their spacecraft after walking on the lunar surface. The lunar dust, the fine powder that covers the Moon and clings to everything it touches, has a smell. Now, you can't smell anything in the vacuum of space, of course. There's no air to carry scent molecules to your nose. But when the astronauts came back inside their lunar module after their moonwalks, when they removed their helmets and began to clean the dust from their suits and equipment, they noticed a distinct odor. And multiple astronauts across different missions described it the same way. Burnt gunpowder. The Moon smells like burnt gunpowder. Scientists believe this smell comes from the chemical composition of the dust and the way it reacts when it comes into contact with oxygen and moisture in the spacecraft's atmosphere. Lunar dust is created by billions of years of meteorite impacts that have pulverized the surface rock into an incredibly fine powder, and this dust contains various minerals and possibly tiny particles of metal. When exposed to Earth's atmosphere after being in the vacuum of space, these materials may undergo chemical reactions that produce the distinctive smell. It's one of those small, unexpected details that reminds us how different the Moon really is from Earth, even though we can see it from our backyard. And speaking of those Apollo missions of human footprints on another world, there's something both beautiful and haunting about the marks we left on the Moon's surface. When Neil Armstrong took his first steps on the lunar soil in July 1969, when he and Buzz Aldrin walked around in the 1/6 gravity, setting up equipment and collecting samples, they left footprints in the dust. Deep, clear impressions of their boots. And those footprints are still there. They will be there for millions of years. Because the Moon has no atmosphere, there is no wind to blow the dust around and erase the footprints. There is no rain to wash them away, no flowing water to smooth them over. The Moon's surface is shaped primarily by meteorite impacts, and while micrometeorites constantly bombard the lunar surface, the process of erosion is so slow that those boot prints, along with the tracks from the lunar rovers and all the other marks left by the Apollo astronauts, will remain visible for far longer than any monument humans have built on Earth. Long after our cities have crumbled to dust, long after the pyramids have weathered away, those footprints on the moon will still be there, preserved in the airless silence, a testament to the first time humanity reached beyond our home world and set foot on another. Earth is not the only rocky planet with moons, though. As we noted earlier, Mars also has companions, two small moons named Phobos and Deimos. These names come from Greek mythology. Phobos means fear and Deimos means dread, the twin sons and attendants of the god of war, fitting companions for the planet named after Mars. But Phobos and Deimos are very different from Earth's moon. They are tiny, irregularly shaped objects that look more like potatoes than spheres. Phobos, the larger of the two, has a diameter of only about 22 kilometers at its widest point. Deimos is even smaller at roughly 12 kilometers across. These are not worlds shaped by their own gravity into round forms. They are just chunks of rock, and their irregular shapes and dark rocky compositions have led scientists to believe that they are not true moons at all, not in the sense that our moon is. Instead, Phobos and Deimos are almost certainly captured asteroids. Early in Mars's history, these two rocks were likely orbiting the Sun in or near the asteroid belt, following their own paths through the solar system, when they happened to pass close to Mars. The red planet's gravity reached out and grabbed them, pulling them into orbit, and there they have remained for billions of years, circling Mars in the darkness. Phobos orbits very close to Mars, so close that it completes one orbit in just 7 hours and 39 minutes. It's moving faster than Mars rotates, which means that if you stood on the Martian surface and watched Phobos, you would see it rise in the west and set in the east, crossing the sky in the opposite direction of the Sun. And Phobos is slowly getting closer to Mars. Tidal forces are gradually dragging it inward, and in about 50 million years, it will either crash into the Martian surface or, more likely, be torn apart by gravitational stresses, creating a temporary ring around the red planet. Deimos, orbiting farther out, will likely remain in place for much longer, a silent companion to a world that may once have been more like Earth, with flowing water and a thicker atmosphere, but is now a cold desert, its two small moons the only witnesses to its transformation. This region of the solar system, the asteroid belt and the moons of the inner planets, represents a transition zone, a place where the remnants of planetary formation mix with fully formed worlds and their captured or collision-born companions. It's a reminder that the solar system is not a static, orderly place but a dynamic realm shaped by gravity and chance, by violent impacts and near misses, by objects captured and worlds torn apart. As we prepare to continue our journey outward, to cross this barrier and enter the realm of the giant planets, we carry with us an understanding that even the spaces between the planets are filled with stories, with objects both large and small that each have their own history written in rock and ice. The asteroid belt stands as a boundary, but also as a connection, linking the warm inner system with the cold outer reaches that await us ahead. Act 4. The Realm of the Giants. Beyond the asteroid belt, beyond the boundary that separates the small rocky worlds from what lies farther out, the solar system changes dramatically. The sun's light here is dimmer, its warmth more distant, and the planets themselves are fundamentally different from those we've explored so far. We are entering the realm of the giants, worlds so large that they dwarf the terrestrial planets, spheres not of rock and metal but of gas and liquid, swirling atmospheres thousands of kilometers deep with no solid surface to stand upon. And ruling over this domain, king of all the planets, is Jupiter. Jupiter is almost difficult to comprehend in its enormity. It is the largest planet in our solar system, so massive that if you could somehow gather together all the other planets, every single one of them, Mercury and Venus and Earth and Mars and Saturn and Uranus and Neptune, all of them combined, and place them on one side of a cosmic scale, Jupiter alone would outweigh them all. In fact, Jupiter is more than twice as massive as all the other planets put together. Its mass is so great that the center of gravity between Jupiter and the Sun, what astronomers call the barycenter, actually lies outside the Sun's surface. In other words, Jupiter and the Sun don't really orbit a point at the Sun's center. They both orbit a point in space just above the Sun's surface, a sort of mutual dance between a star and a planet so large it begins to blur the line between planet and something more. If Jupiter had been about 80 times more massive, if there had been just a bit more material available in its region of the early solar system, it would have ignited nuclear fusion in its core and become a star itself, and we would live in a binary star system rather than one with a single sun. As it is, Jupiter remains a planet, but one that exerts enormous influence over everything around it, shaping the orbits of asteroids, deflecting comets, and protecting the inner solar system from some impacts while directing others inward. Jupiter's appearance is striking even through a small telescope. The planet is covered in bands of clouds, alternating stripes of cream, brown, orange, and white that circle the globe parallel to the equator. These bands are created by Jupiter's incredibly rapid rotation. Despite being so massive, Jupiter spins faster than any other planet in the solar system, completing one full rotation in just under 10 hours. This rapid spin creates powerful winds and jet streams in the planet's atmosphere, and these winds sort the clouds into the distinctive bands we see. The lighter-colored zones are regions where gas is rising from below, cooling and forming high-altitude clouds. The darker belts are areas where gas is sinking, revealing deeper, warmer layers of the atmosphere. And within these swirling clouds, storms rage, some of them larger than entire planets. The most famous of these storms is the Great Red Spot, an oval-shaped anticyclonic storm that has been observed continuously since at least 1830, though it may be much older than that. Some astronomers believe it could have been raging for over 300 years. 3 centuries of continuous storm. The Great Red Spot is so large that you could fit Earth inside it with room to spare. At its widest, it spans about 16,000 kilometers, though recent observations show it has been shrinking slowly over the past few decades. This storm is essentially a massive high-pressure region in Jupiter's atmosphere, spinning counterclockwise with wind speeds reaching up to 430 kilometers per hour at its edges. The reddish color, which has varied in intensity over the years, may come from complex organic molecules created by the interaction of sunlight with chemicals in Jupiter's atmosphere, though the exact mechanism is still being studied. Standing in a spacecraft at the edge of the Great Red Spot, looking down into that swirling mass of clouds, you would see towers of gas rising and falling, lightning flashing in the depths, and storms within storms, a churning system of atmospheric dynamics that has outlasted entire civilizations on Earth and shows no signs of stopping. Jupiter has another claim to fame beyond its size and storms. It has a remarkable collection of moons. At last count, Jupiter has over 90 known moons, ranging from tiny irregular chunks of rock only a few kilometers across to large geologically active worlds. The four largest of these moons, discovered by Galileo Galilei in 1610 when he pointed his newly constructed telescope at Jupiter, are worlds in their own right. Io, the innermost of the four, is the most volcanically active body in the entire solar system, its surface constantly being resurfaced by sulfurous lava flows driven by intense tidal heating from Jupiter's gravity. Ganymede, the largest moon not just of Jupiter but of the entire solar system, is bigger than the planet Mercury and has its own magnetic field. Callisto, the outermost of the Galilean moons, is ancient and heavily cratered, its surface a record of billions of years of impacts. But it's the second of these moons, Europa, that has captured the attention of scientists searching for life beyond Earth. Europa is slightly smaller than our moon, a world of ice and rock locked in a gravitational dance with Jupiter. But beneath Europa's frozen surface, beneath a shell of ice that may be 10 to 15 kilometers thick in places, scientists believe there lies a global ocean of liquid water. An ocean that could contain twice as much water as all of Earth's oceans combined. The evidence for this hidden ocean comes from multiple sources. Europa's surface is crisscrossed with long cracks and ridges, and relatively few impact craters, suggesting the ice is young and constantly being renewed from below. The way Europa interacts with Jupiter's powerful magnetic field suggests a layer of electrically conductive material, like salty water, beneath the ice. And images from spacecraft have shown what appear to be plumes of water vapor erupting from the surface, possible geysers breaking through the ice from the ocean below. If this ocean exists, and most scientists now believe it does, it's kept liquid by the same tidal heating that powers Io's volcanoes. As Europa orbits Jupiter, the giant planet's gravity flexes and needs the moon's interior, generating heat through friction. This heat could keep the ocean liquid, and it could provide energy that life might use. On Earth, we've found entire ecosystems thriving in the deep ocean around hydrothermal vents, places where no sunlight penetrates but where heat and chemicals from within the planet support communities of bacteria, tube worms, and other creatures. Could something similar exist in Europa's dark ocean? We don't know, but Europa has become one of the prime targets in the search for life beyond Earth, a frozen moon hiding what might be one of the most habitable environments in the solar system beneath its icy shell. Continuing outward from Jupiter, we come to what is perhaps the most visually stunning planet in our solar system: Saturn, the ring planet. Even in ancient times, before telescopes, Saturn was known as a wandering star, but it wasn't until Galileo first observed it in 1610 that something unusual was noticed. Though his telescope wasn't powerful enough to clearly make out the rings, and he described Saturn as having ears. It was later astronomers who realized that Saturn was surrounded by a magnificent system of rings, bright and extensive, circling the planet's equator. These rings are Saturn's defining feature, the characteristic that makes it instantly recognizable, and they are truly magnificent. They extend outward from the planet for hundreds of thousands of kilometers, yet in most places they are astonishingly thin, sometimes less than 10 meters thick. It's as if someone took a disk of material and stretched it out into a vast, flat plain surrounding the planet. What are these rings made of? For many years, scientists debated this question, but we now know the answer. Saturn's rings are composed almost entirely of water ice. 99.9% pure water ice, in fact, ranging from tiny particles the size of grains of sand to chunks as large as houses, all orbiting Saturn in a flat disk. These countless pieces of ice reflect sunlight brilliantly, making the rings bright and visible even from Earth with a modest telescope. The origin of the rings is still debated. They might be the remnants of a moon that wandered too close to Saturn and was torn apart by tidal forces, or they might be leftover material from Saturn's formation that never coalesced into a moon. Recent evidence from the Cassini spacecraft, which orbited Saturn from 2004 until 2017, suggests the rings might be relatively young, perhaps only a few 100 million years old, far younger than Saturn itself. This means the rings we see today might not be a permanent feature, but rather a temporary decoration, and we are fortunate to be alive at a time when Saturn wears this spectacular crown. Saturn itself, like Jupiter, is a gas giant, a world with no solid surface, just layers upon layers of atmosphere transitioning gradually into liquid and then into exotic forms of matter under immense pressure deep in the interior. But Saturn has a remarkable property that sets it apart from every other planet. It has the lowest density of any planet in the solar system. Saturn's density is less than that of water. In fact, Saturn's average density is about 0.69 grams per cubic centimeter, while water has a density of 1 gram per cubic centimeter. This has led to a popular and amusing thought experiment. If you could find a bathtub large enough to hold a planet 60,000 kilometers in diameter, and if you could fill that bathtub with water, Saturn would float. It would bob on the surface like a gigantic beach ball, the only planet in our solar system light enough to perform this trick. Of course, Saturn would leave quite a ring around the tub as its ice rings melted, but the mental image is delightful nonetheless. This low density tells us something about Saturn's composition. It's made primarily of hydrogen and helium, the lightest elements in the universe, with only a small rocky core deep in its center, giving it a much lower overall density than the rocky terrestrial planets or even than Jupiter, which has more heavy elements mixed into its composition. Saturn, like Jupiter, has an extensive family of moons, over 80 at last count. And among these moons is one that stands out as perhaps the most intriguing world in the entire solar system: Titan. Titan is Saturn's largest moon, bigger than the planet Mercury, and it holds a unique distinction. It is the only moon in the solar system with a thick atmosphere. Not a thin wisp of gas, but a substantial atmosphere, thicker even than Earth's. If you descended through Titan's atmosphere in a spacecraft, you would feel the pressure increasing steadily as you dropped lower, and by the time you reached the surface, the atmospheric pressure would be about 1.5 times that at Earth's sea level. This atmosphere is mostly nitrogen, about 98%, with small amounts of methane and other organic compounds. And that methane plays a role on Titan that water plays on Earth. Because Titan is so far from the sun and so cold, with surface temperatures around -179 degrees Celsius, methane can exist as a solid, liquid, and gas. And on Titan, methane goes through a cycle very similar to Earth's water cycle. Methane evaporates from the surface, forms clouds in the atmosphere, and falls as rain, creating rivers that flow into lakes and seas. Titan has lakes, actual bodies of liquid on its surface, but they're not filled with water. They're filled with liquid methane and ethane. The Cassini spacecraft mapped these lakes in Titan's polar regions, and they are substantial. Kraken Mare, the largest of these methane seas, is larger than the Caspian Sea on Earth. Imagine standing on Titan's surface, looking out over a vast lake of liquid methane under an orange sky, the thick atmosphere scattering the sunlight and giving everything a strange, hazy appearance. It's a world where the familiar processes of evaporation and precipitation of rivers and lakes, play out with an entirely different substance, a world that is both alien and oddly familiar at the same time. Venturing even farther from the Sun into regions where sunlight is merely a bright star in the sky rather than the warm glow we know on Earth, we encounter two ice giants, worlds fundamentally different even from Jupiter and Saturn. The first of these is Uranus, a planet so unusual that it immediately stands out even among the oddities of our solar system. Uranus rotates on its side. While most planets spin roughly upright, with their axes of rotation nearly perpendicular to the plane of their orbits, Uranus is tilted over by 98 degrees. This means its axis of rotation is nearly parallel to its orbital plane, causing the planet to roll around the Sun like a ball rather than spinning like a top. This extreme tilt has strange consequences. During Uranus's 84-year orbit around the Sun, each pole experiences 42 years of continuous sunlight followed by 42 years of continuous darkness. Imagine seasons that last for decades, where summer means the sun never sets and winter is an endless night. Scientists believe this bizarre orientation is the result of a massive collision early in Uranus's history, an impact with an Earth-sized body or perhaps multiple large impacts that literally knocked the planet over onto its side. The planet never recovered its upright orientation, and so it continues its sideways journey around the Sun, a permanent reminder of the violent chaos of the early solar system. Uranus and its companion ice giant Neptune are different in composition from Jupiter and Saturn. While the gas giants are mostly hydrogen and helium, Uranus and Neptune have much more water, methane, and ammonia mixed into their interiors, often in exotic high-pressure forms that don't exist naturally on Earth. And within these strange interiors, under the crushing pressures that exist thousands of kilometers deep in these planets' atmospheres, something remarkable may be happening. Scientists have theorized, and some laboratory experiments have supported, the idea that deep within Uranus and Neptune, it may actually rain diamonds. The intense heat and pressure at these depths could break apart methane molecules, freeing carbon atoms, and then crush that carbon into crystalline form. Diamonds. These diamonds might form as small crystals that grow as they sink deeper into the planet, potentially creating a layer of liquid diamond or even accumulating into a solid diamond layer around the planet's core. It sounds like science fiction, like something from a fantasy novel, but the physics supports it, and it's quite possible that these distant ice giants have treasures within them beyond imagination, forever out of reach in the crushing depths of their interiors. Finally, at the edge of the classical solar system, nearly 4.5 billion kilometers from the Sun, orbits Neptune. The most distant of the 8 planets, Neptune is a deep blue world, colored by methane in its atmosphere that absorbs red light and reflects blue. It's a cold, dark place where the Sun appears over 1,600 times dimmer than it does from Earth, but despite the cold and distance, Neptune is far from quiet. This planet has the fastest winds in the entire solar system. While Jupiter's Great Red Spot has impressive winds reaching 430 kilometers per hour, Neptune's winds scream through its atmosphere at speeds exceeding 2,100 kilometers per hour. 2,100 kilometers per hour. That's faster than the speed of sound on Earth. These supersonic winds whip around the planet, creating storms and cloud features that appear and disappear over time. One such storm, observed by Voyager 2 in 1989 and called the Great Dark Spot, was about the size of Earth, though it had vanished by the time the Hubble Space Telescope looked for it a few years later. What drives these incredible winds on such a distant, cold world is still not entirely understood, but it likely has to do with heat escaping from Neptune's interior combined with the planet's rapid rotation and the way its atmosphere circulates that energy. Neptune holds another special distinction in the history of astronomy. It was the first planet to be discovered not by accident, not by someone scanning the sky and noticing a new object, but by mathematical prediction. In the early 1800s, astronomers studying Uranus noticed something odd. The planet wasn't quite where their calculations said it should be. Its orbit was slightly off, as if some unseen force was tugging at it. Two mathematicians, Urbain Le Verrier in France and John Couch-Adams in England, independently worked on the problem and came to the same conclusion. There must be another planet beyond Uranus, and its gravity was affecting Uranus's orbit. They calculated where this unknown planet should be, and in September of 1846, astronomers pointed their telescopes to the predicted location, and there it was. Neptune. A new world found not with eyes but with mathematics, a triumph of human reason and our understanding of gravity and orbital mechanics. It was a profound moment in the history of science, proof that the laws of physics we discovered on Earth applied throughout the universe, and that with enough understanding, we could predict the existence of worlds we had never seen. These giant planets, Jupiter and Saturn and Uranus and Neptune, are worlds of superlatives, of extremes in size and speed and strangeness. They are so different from the rocky planets of the inner solar system that they seem almost to belong to a different category of object entirely, and in many ways they do. They are miniature solar systems unto themselves, each one surrounded by dozens of moons and, in the case of all four giants, by ring systems, though none as spectacular as Saturn's. They are worlds we can never walk upon, whose true surfaces, if they exist at all, lie buried under thousands of kilometers of atmosphere and liquid, forever inaccessible. And yet they are magnificent, beautiful in their own right, from Jupiter's swirling clouds and ancient storm to Saturn's gleaming rings, from Uranus rolling on its side to Neptune's deep blue hue and howling winds. They remind us that our solar system is a place of diversity beyond imagination, where each world is unique, shaped by its own history, its own chemistry, its own set of circumstances into something unlike anything else in existence. Act V. The icy fringes and beyond. We have traveled far from the sun's warmth, far from the bright center of our solar system where the rocky planets orbit. We have passed through the realm of the giants, those immense worlds of gas and ice that dwarf everything in the inner system. But our journey is not yet complete. Beyond Neptune, beyond the orbit of the most distant classical planet, the solar system does not simply end. Instead, it fades gradually into the darkness, extending outward into regions so distant and cold that sunlight becomes little more than a bright star among many. Here, in these frozen outer reaches, in the twilight zone between our sun's domain and the vast emptiness between stars, lie worlds and objects we are only beginning to understand. This region beyond Neptune is known as the Kuiper Belt, named after astronomer Gerard Kuiper, who predicted its existence in the 1950s. The Kuiper Belt is similar in some ways to the asteroid belt between Mars and Jupiter, a region filled with countless small bodies, remnants of the solar system's formation. But where the asteroid belt is made primarily of rock and metal, the Kuiper Belt is a realm of ice. Out here, so far from the sun's heat, water ice, methane ice, and ammonia ice are common, mixed with rock to form objects that have remained frozen for over 4 billion years, pristine samples of the material from which our solar system formed. The Kuiper Belt begins at roughly the orbit of Neptune, about 4.5 billion kilometers from the Sun, and extends outward for another 3 billion kilometers or more. It's a vast, donut-shaped region, and within it orbit perhaps hundreds of thousands of objects larger than 100 kilometers across, with countless smaller pieces as well. And among these icy bodies, one in particular has captured human imagination and sparked controversy and affection in equal measure: Pluto. For 76 years from its discovery in 1930 until 2006, Pluto was considered the ninth planet of our solar system, the smallest and most distant, orbiting far beyond Neptune in the cold and dark. Generations of people grew up learning that our solar system had 9 planets, with little Pluto bringing up the rear. But as our telescopes improved and we discovered more objects in the Kuiper Belt, some of them nearly as large as Pluto, astronomers faced a dilemma. Either we would have to start calling these newly discovered objects planets too, potentially giving us dozens of planets, or we needed to create a new category. In 2006, the International Astronomical Union made the controversial decision to reclassify Pluto as a dwarf planet, a category for objects that are large enough to be rounded by their own gravity but haven't cleared their orbital neighborhood of other debris. Many people were upset by this decision. Pluto had been the underdog planet, the little world at the edge of the system, and it felt to many like a demotion. But reclassification didn't make Pluto any less interesting or important. It's still a world in its own right, a fascinating place we knew very little about until recently. That changed in July of 2015 when NASA's New Horizons spacecraft, after a journey of more than 9 years covering over 5 billion kilometers, made a close flyby of Pluto. The images it sent back were stunning, revealing a world far more complex and geologically active than anyone had expected. Pluto's surface is varied, with regions of ancient, heavily cratered terrain alongside areas that appear young and smooth, resurfaced by geological processes in the relatively recent past. There are mountains made of water ice that reach heights of 3.5 kilometers, rising from plains of frozen nitrogen. And perhaps most striking of all, on Pluto's surface, clearly visible even from space, is a massive glacier in the shape of a heart. This feature, informally named Tombaugh Regio after Clyde Tombaugh who discovered Pluto, is about 1,600 kilometers across, roughly the size of Texas and Oklahoma combined. The western lobe of this heart, called Sputnik Planitia, is a vast plain of frozen nitrogen, carbon monoxide, and methane. This plain appears to be geologically active even today, with the frozen nitrogen slowly circulating in massive convection cells, like a lava lamp in extremely slow motion, constantly resurfacing the area and erasing impact craters. Here, on this tiny world orbiting in the frozen outer reaches of our solar system, billions of kilometers from the Sun, geological processes are still at work, shaping and reshaping the surface. Pluto is not a dead, unchanging ball of ice. It's a dynamic world with a complex atmosphere that freezes and falls to the surface when Pluto is farthest from the Sun in its elliptical orbit, then sublimates back into gas as Pluto approaches closer to the Sun's distant warmth. It's a world that surprised us, that exceeded our expectations, and that reminded us that even the smallest worlds can be extraordinary. But Pluto is just one member of a much larger population. The Kuiper Belt extends far beyond Pluto's orbit, and beyond the Kuiper Belt lies something even more vast and mysterious: the Oort cloud. This is a theoretical shell of icy debris, a spherical cloud of perhaps trillions of objects surrounding our entire solar system. We say theoretical because we have never directly observed the Oort cloud. It's too far away, the objects within it too small and dark to see with current telescopes. But we believe it exists because of the comets that occasionally fall inward toward the Sun from all directions, including from angles far above and below the plane where the planets orbit. These long-period comets that take hundreds or thousands or even millions of years to complete one orbit around the Sun, must come from somewhere, and the Oort cloud is the somewhere we've calculated. This shell of icy bodies is thought to begin somewhere between 2,000 and 5,000 times Earth's distance from the Sun and extend outward to perhaps 100,000 times that distance. At its outer edge, the Oort cloud reaches about 1.6 light-years from the Sun. To put that in perspective, it would take light traveling at 300,000 kilometers per second, 1.6 years to cross from the Sun to the outer edge of the Oort cloud. This is halfway to the nearest star. The Oort cloud represents the very edge of our Sun's gravitational influence, the boundary between what belongs to our solar system and what belongs to the vast interstellar space beyond. The Oort cloud is thought to be populated by objects left over from the formation of the solar system, icy bodies that formed closer to the Sun but were flung outward by gravitational interactions with the giant planets, particularly Jupiter and Saturn, in the chaotic early days of our cosmic neighborhood. They settled into this distant reservoir, orbiting so far from the Sun that they are barely bound to it at all, vulnerable to perturbations from passing stars or the gentle tidal pull of the Milky Way galaxy itself. Occasionally, something disturbs one of these icy bodies, a gravitational nudge from a passing star perhaps, or the slow influence of galactic tides, and it begins to fall inward toward the Sun on a journey that may take millions of years. As it approaches the inner solar system, as it draws closer to the Sun's heat, the ice begins to sublimate, turning directly from solid to gas without passing through a liquid phase. This gas streams away from the comet, carrying dust particles with it, and sunlight reflecting off this gas and dust creates the spectacular tail we associate with comets. Comet tails are beautiful, ethereal things, sometimes stretching for millions of kilometers across the sky, glowing softly in the reflected sunlight. But there's something interesting about these tails, something you might not expect if you thought about how tails usually work. A comet's tail doesn't trail behind it as it moves through space, the way smoke trails behind a plane. Instead, a comet's tail always points away from the Sun, regardless of which direction the comet is traveling. As a comet approaches the Sun, its tail streams out behind it. But as it rounds the Sun and begins its outward journey, the tail actually precedes the comet, pointing ahead in its direction of travel. This happens because the tail isn't created by the comet's motion through space. It's pushed by the solar wind, that constant stream of charged particles flowing outward from the Sun. The solar wind and the pressure of sunlight itself blow the gas and dust away from the comet in the direction away from the Sun, creating a tail that always points in the antisolar direction. It's a visible reminder of the Sun's influence extending far out into space, reaching even these distant travelers from the Oort cloud. As we contemplate these distant regions, these frozen objects drifting in the darkness at the edge of the Sun's influence, it's worth reflecting on the nature of the space between them. We often think of space as empty, and in many ways it is. The vacuum of space is far more empty than any vacuum we can create on Earth. Between the planets, between the stars, matter is spread so thinly that for all practical purposes, there is nothing there. And in this nothingness, in this near-perfect vacuum, one consequence is silence. Complete and utter silence. Sound, as we experience it, is a wave traveling through a medium, whether that medium is air or water or the solid material of a wall. The molecules of that medium vibrate and bump into each other, transmitting the energy of the sound wave from one place to another. But in space there are no molecules. There is no medium for sound to travel through. An explosion in space would produce no sound. A spacecraft firing its engines would be silent to an observer floating nearby, even if that observer could somehow survive the vacuum. The great collisions that formed our planets, the impacts that scarred Mercury and the Moon, the supersonic winds that race around Neptune, all of these happened and continue to happen in absolute silence. It's a strange thought that the cosmos is soundless, that all the violence and beauty and activity of stars and planets and galaxies unfolds without making a whisper. The only sounds of space are the ones we create ourselves, inside our spacecraft and spacesuits, or the ones we synthesize from other types of data, converting radio waves or other electromagnetic signals into audio frequencies our ears can hear. The universe is a silent theater, and we are among the few types of matter organized in such a way as to even care about sound. But humanity has not been content to simply observe the cosmos from our home planet. We have sent our emissaries out into this silent realm, robotic explorers that have visited every planet in our solar system and traveled far beyond. And among these explorers, two spacecraft hold a special place. Voyager 1 and Voyager 2, twin probes launched in 1977 to take advantage of a rare alignment of the outer planets. These spacecraft visited Jupiter and Saturn, with Voyager 2 continuing on to Uranus and Neptune, completing humanity's first grand tour of the solar system. But their missions didn't end there. After their planetary encounters, the Voyagers continued outward, heading toward the edge of the solar system and beyond. And in August of 2012, Voyager 1 crossed a boundary that no human-made object had ever crossed before. It left the heliosphere, the bubble of charged particles and magnetic fields created by the Sun, and entered interstellar space, the space between the stars. Voyager 1 is now the most distant human-made object, currently traveling through the darkness more than 24 billion kilometers from Earth. At that distance, radio signals from Voyager 1, traveling at the speed of light, take over 22 hours to reach us. The spacecraft is so far away that the Sun, from Voyager 1's perspective, is just another star in the sky, no longer the bright disk that dominates our daytime view. And both Voyager spacecraft carry with them something extraordinary. A message, a greeting, a hope. Attached to each Voyager is a 12-inch gold-plated copper phonograph record, known as the Golden Record. This record contains sounds and images selected to portray the diversity of life and culture on Earth, a sort of time capsule and message in a bottle combined, sent out into the cosmic ocean. The record includes greetings in 55 different human languages, from ancient Akkadian to modern Mandarin Chinese. It contains sounds from nature, the surf of oceans, wind and thunder, the songs of birds and whales, the sounds of a human heartbeat and laughter and a mother's kiss. There is music, a collection ranging from Bach to Beethoven to Chuck Berry, traditional songs from cultures around the world, the sounds of humanity expressing itself through melody and rhythm. And there are images, 116 of them, encoded in analog form on the record, showing mathematical and physical quantities, the solar system, human anatomy, pictures of people and places and activities from across our world. Instructions for playing the record are etched on its cover, along with a diagram showing Earth's location in the galaxy using pulsars as reference points. The Golden Record will likely outlast everything we have built on Earth. Long after our cities have crumbled, long after our species has either transformed into something new or passed into extinction, Long after the continents have drifted into new configurations and the Sun has begun its transformation into a red giant, the Voyager spacecraft will still be out there, drifting through the galaxy, carrying their golden disks. In billions of years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445. Of course, by that time the spacecraft will be long dead, its power source exhausted, its transmitters silent, a derelict monument tumbling through the void. But the record will remain intact, gold being one of the most stable and corrosion-resistant materials we know. And if, someday, somewhere, some other intelligence finds it, if some curious mind in some distant future discovers this artifact from an extinct civilization and deciphers the instructions and plays the record, they will hear the sounds of Earth. They will hear our music and our languages. They will see images of the world that created the Voyagers. They will know for a moment that we existed, that we looked up at the stars and wondered if we were alone, that we sent this message not knowing if anyone would ever receive it, but hoping, always hoping. It's a humbling thought, isn't it? For all our achievements, for all the spacecraft we've sent out and the telescopes we've built, for all the images we've captured and the data we've gathered, we have only explored about 1% of our own solar system. 1%. There are moons we've never visited, asteroids we've only glimpsed from a distance, vast regions of the Kuiper Belt and the Oort cloud we know almost nothing about. The solar system is immense beyond our everyday comprehension, and we are just beginning to explore it, just starting to understand the diverse collection of worlds and objects that share the Sun's gravitational embrace with us. Every mission reveals surprises. Every new observation challenges our assumptions. Every world we visit in detail turns out to be more complex, more interesting, more worthy of study than we imagined from afar. The tiny fraction we've explored has already shown us wonders beyond measure. What lies waiting in the 99% we haven't yet reached? What strange moons and bizarre objects and unexpected phenomena are out there in the darkness, orbiting unseen, waiting for the day when human eyes or instruments finally turn their attention in that direction? We stand at the beginning of an age of exploration that could last for centuries or millennia, an age in which humanity reaches outward from its cradle world to touch and study and perhaps one day inhabit the other worlds of our solar system. We have sent our robots to Mars, and they have shown us a world that was once wetter and perhaps more hospitable, a world where conditions might have allowed life to emerge in the distant past. We have glimpsed the subsurface ocean of Europa and wondered what might live in those dark waters. We have seen the methane lakes of Titan and imagined what strange chemistry might be occurring on that distant moon. We have been surprised by the geology of Pluto and humbled by the power of Jupiter's storms. And all of these discoveries and wonders exist within our own cosmic neighborhood, within the small patch of space bound to our Sun. Beyond lies the rest of the galaxy, hundreds of billions of stars, many of them with their own planetary systems, their own stories of formation and evolution playing out across the eons. And beyond our galaxy lie billions of other galaxies, each a universe unto itself, filled with stars and worlds beyond counting. But for now, for this moment, as we lie here in the darkness allowing our minds to wander through the solar system, from the Sun's nuclear furnace to the icy darkness of the Oort cloud, we can feel both small and connected. Small because we are tiny beings on a tiny world orbiting an ordinary star in an ordinary galaxy, our entire history a brief moment in the cosmic timeline. But connected because we are made of the same matter as everything else in the universe, atoms forged in the hearts of ancient stars, organized by chance and time and the laws of physics into forms capable of thought and wonder. We are the universe becoming conscious of itself, matter awakening to contemplate its own existence. And in that, there is something beautiful, something worth celebrating as we drift towards sleep, secure in the knowledge that we are part of something vast and ancient and ongoing, part of the great cosmic story that began with the Big Bang and continues today in every star that shines, every planet that orbits, every moon that reflects the light of its parent world. We are part of it all. And as you close your eyes and let sleep take you, perhaps you can carry with you a sense of that connection, that belonging to something greater than ourselves, that quiet wonder at the magnificent, mysterious, beautiful solar system we call home.